Okay, very good. So I think we can get started. So I'll be telling you about explorations in string theory, which basically will be a course on advanced quantum field theory and on some applications of quantum field theory, various aspects of advanced quantum field theory. Most notably, we will cover something known as holography and ADS-CFT, which is very much related to string theory, but which is much broader than string theory, as we will see. It's basically one of the modern tools in quantum field theory. And we will be covering, most of the lectures will be about holography and about ADS-CFT, and how do we think about ADS-CFT. And I'll be giving the first 2 weeks. So I'll start with some reminder of what is string theory and some cartoonish picture of string theory. So the level of rigor will increase monotonically, and then it will probably decrease a little bit towards the end of the first 2 weeks. And then Freddy will pick up in the third week, and he will talk about entanglement entropy, and in particular entanglement entropy related to ADS-CFT and how does it emerge within ADS-CFT. So we'll start, as I said, with an introduction, some motivation towards having holographies. Then we will move to the study of correlation functions, in particular study of correlation functions of local operators within holographic theories. And then we will move to non-local observables in quantum field theory, and then Freddy will pick up with one example of such non-local observables. Okay, so do interrupt me if you have any questions. And today, as I said, we are going to mostly hand wave a little bit and remind you of a couple of cool things about string theory, but mostly at the level of pictures and so on. Most of you, or many of you, have heard already about these things in the string theory course. But if you did not, you might have seen it in Wikipedia or in any popularization book or something. It really is general stuff that you probably heard about, at least at a cartoonish level. So let's start. So what is the string S matrix, which, if you want, is the definition of string theory? Well, the definition of string theory, of perturbative string theory that we have, tells us the following. Suppose I want to study the interaction of 3 strings. So I draw this kind of pair of pants diagram, and I want to study the interaction of these 1, 2, 3 strings. Let n be the number of external strings. And what am I instructed to do? I'm instructed to sum over all possible ways 3 strings can interact, which means that they can draw a pair of pants, or they can draw a pair of pants with genus 1, or higher genus configurations. And what this cartoon means I should sum over all possible such surfaces which have no holes, or which have 1 hole, or which have 2 holes, and so on. And as we will see, they come weighted by some coupling, some string coupling, like some vertex, like in Feynman diagram. So if there is a cubic vertex, it comes with some G string. But if it has a hole, it comes with a higher power of G string. In this case, it will be G string cubed, and so on and so forth. G string to the 5, to the 7, and so on. This is an example for this cubic amplitude. So let's make a few comments about these things. So first thing, one of the beautiful things about string theory, which was one of the things that people liked a lot in the 80s when string theory first appeared, was that if you think a bit from a quantum field theory point of view, if you imagine that each string would be like a particle seen from very far away, what would this diagram be? This diagram would be something like this diagram, for example, where I have 3 particles and there is a loop. Well, but there are other diagrams for 3 particles with a loop as well. For example, we could have this diagram, right? Or this diagram. And one of the beautiful things about string theory is that if you imagine taking these field theory diagrams where you have a point particle and fatten each particle into a tube, then all these diagrams have the same topology. By integrating over all possible shapes of these tubes, I take into account all diagrams at once. So all these diagrams, they are all, and I will underline all, contained in a single string topology. So this is one of the very appealing features of string theory. It's very economical. If I draw if I studied string topologies with one loop, with one hole, I take into account all diagrams that have one hole in them. Another cute thing is that you see, in field theory, you have this point and you have this point, and something dangerous happens when these 2 points approach, right? So when this distance d goes to 0, this is a dangerous ultraviolet region where things blow up and you need to renormalize your theory and so on. It's a short distance singularity. But if I fatten this, there's no such notion. There's no Lorentz invariant notion of which distance is becoming small if I start fattening it and asking when are these points. Well, there is no analog of this point. Everything becomes softened. Everything becomes smoothened out. I just have some joints of some tubes, and there's no such notion of when these interaction points are meeting, because if I fatten, there is no such notion of interacting point anymore. So in string theory, there is no such dangerous UV region from the point of view of these diagrams, and indeed they are UV finite. So this is one of the very beautiful things about string theory. It's a theory which is UV finite because we no longer have localized interaction points where we get in trouble because of UV divergences. All these diagrams are captured in a single topology. But even more than that, let me remind you that if you zoom on a leg, suppose I zoom on a leg, and what is this leg? Well, this leg can be some string, it's a cylinder coming in, or it can be a cylinder, a string which is oscillating more. And the intuition is that these different oscillation patterns of the string describe different particles. If I zoom out, then this very oscillating string will have bigger energy because it will have the energy of the string plus this vibrational energy. So all these describe different particles which become heavier as I consider more and more excited modes. So string theory describes infinitely many different particles at once. So this is the third nice feature of string theory, that by studying different vibration patterns of the string, we are learning about various particles from a low energy point of view. And why are they heavier as I go there? Because string theory has some string tension. The tension wants the string to be point-like, wants to shrink the tension, right? It's a piece of rubber. But if the string is vibrating a lot, and if the tension is big, then this costs a big amount of energy. So that's why they are heavier. So this guy here, this higher mode, this guy will be very heavy if the string tension is large. Now, let me also remind you that in practice, how do we compute? This looks like something a bit formidable. So it looks all very nice. I mean, there are many particles, a single diagram, no UV divergences, and so on. But it looks a bit tricky to say, please sum over all surfaces with topology of some pair of pens. Mathematically, why can we do it? Mathematically, why can we do it? Why are things not that complicated? Because the theory, the two-dimensional theory that governs this string theory, is a simple conformal field theory. So in practice, what you do is you consider, say, for example, a sphere. Okay. So this would be a sphere, which is the same as the complex plane. And what we do is we attach 3 tubes to the sphere, right? And this, by this here, we mean we insert some tube which is generated by putting what's called a vertex operator. And I'll be a bit more explicit soon. But the idea is that by you consider a metric on this worldsheet. And because you can choose any metric on the worldsheet, because the theory is conformal, you can consider a metric where most of the interactions happen on some finite sphere. And then to it, you attach some tubes where, say, this line here would be this circle here at some small radius epsilon, and then all this remaining part of this tube asymptotically will be just generated by a tube that I would put there or by a vertex operator. So in practice, what you have to do is you insert here a vertex operator V, which will be something like some integral over the sphere of some so-called unintegrated vertex operator, V of Z and Z bar, and I'll write what this V is in a moment, where each different vertex operator corresponds to each different vibration of the string. So there is one vertex operator for this string which is not very heavy, there is another vertex operator for this string, and so on and so forth. Okay? So what are these vertex operators? These vertex operators of Z and Z bar, let me remind you, they can be several things. So the simplest one is just one which just injects some momentum k. Let me be explicit. So there is some Ka, Xa of Z and Z bar. This is just a vertex operator corresponding to a plane wave. So it just tells me that I'm inserting some state with some definite momentum k. And let's remind ourselves that this A runs from 10 dimension or 26 dimension, depends if it's superstring or bosonic string. So it's a 10-dimensional space-time index. Whereas this thing here are 2-dimension worldsheet coordinates. So which are where we used to parameterize our sphere or parameterize what's called the worldsheet. So we parameterize this sphere, and then we map the sphere to some scalar x, and there are 10 of these scalars, and they form a vector from the point of view of space-time and a scalar from the point of view of the worldsheet. Okay? So it's a beautiful thing that in string theory we can describe 10-dimensional physics in terms of a 2-dimensional conformal field theory. It's really something very deep and very beautiful about string theory. There are other vertex operators that you could construct, like e to the I k dot x, now I'm omitting the indices, times, for example, d of x mu, d bar of x nu. Okay? And this, the first one here, for example, in bosonic string, would describe a tachyon in bosonic string. And the second one would describe a graviton with polarization h mu nu in the direction mu nu. You can contract with some polarization epsilon mu nu if you want to get rid of those indices. And there are many more vertices operators corresponding to the various strings that you could imagine considering as an interaction of. Okay? And this is what string theory, what perturbative string theory is. And soon I'll write a formula, but let me just remind you a couple of simple things about these vertex operators. So is this familiar to everyone? Or even if it's not familiar, is it digestible? I mean, do you understand? We are not going to use it. I just want to remind people what string theory is. We are going to use the intuition that comes from these cartoons, and we are going to use the spirit of it, but not the technical details. The technical details, we will rederive everything from scratch. But I do think it's important to have this kind of physical picture in mind. So this is just a summary of the general physical picture. So is it clear so far? Now, for example, let's just, to practice a little bit, remind ourselves of what's the mass of the graviton, for example. Right? So how would we see the mass of the graviton? So first let's see what's the mass. So what would be the mass of the graviton? You see that for string theory to make sense, if I want to say that I'm integrating over a sphere, then this vertex operator must be invariant under changing z goes to f of z and z bar goes to f bar of z bar. Because it's a conformal transformation, And if I want this to be invariant, the full thing, then this guy V must have the proper weight to absorb the transformation of the measure, such that it doesn't matter which coordinates I'm using, right? So different people parameterize the sphere in different ways. Of course, they should agree on the same result. So this means that this vertex operator should have dimension 2, or rather 1 plus 1, 1 with respect to z, 1 with respect to z bar. If we wanted to transform, if we wanted, together with the measure, to give some vertex operator that is sensible and that's invariant under the ways of parameterizing the sphere. Okay? So the dimension of the scalar x is equal to 0, classically. Right? So I remind you that string theory is just a bunch of free scalars, one per each direction of space-time, right? So the dimension of x in 2 dimensions, a free scalar in 2 dimensions is just 0. If you have a kinetic term dx square, x has dimension 0, right? So it looks like we have a problem, like e to the I kx has dimension 0, and we are in trouble, right? But this is a bit tricky. We have to be careful with quantum effects when we deal with free scalars in 2 dimensions. So I remind you that the correlation function of x with x is a log. If I put one at z and one at w, okay, up to some constant that I'm not working out in detail, depends on the normalization, it's related to the string tension. And it's a Gaussian field, so e to the I kx with e to the I kx, if I consider a 2-point function, right? This would be exponential of the propagator of x with x, because the field is Gaussian, and it will give you something like e to the k square times log of z minus w, okay? Which is equal to 1 over z minus w squared. This is what we want if k squared equal to minus 2. And this tells us that we have a tachyon with k squared equal minus 2. Okay? So for these objects to make sense, I cannot inject any momenta. I must inject a momenta with a mass square which is minus 2. Okay? If the mass square is minus 2, I'm injecting a vertex operator of the right dimension. Okay? So this is the tachyon. What about the graviton? Well, we would have to check more carefully, compute again the 2-point function of this vertex operator with itself. But now that we have already some experience, we can see right away what will happen. We have a d and a d bar. So the dimension of d plus the dimension of d bar is equal to 2. So it's already good. So we want the rest to have dimension 0. So x has dimension 0. E to the I kx has dimension k squared. So it adds up to 0. So if k squared equal to 0. If you want the dimension of the rest to be 0. And that's how we see that the graviton has mass 0. Okay? So string theory is a theory that contains in particular this spin 2 particle with 0 mass, which is called the graviton. And that's another reason why people like string theory a lot, because it's a candidate for a theory of quantum gravity. Okay, good. So this is just some string theory. So let's continue and write this equal sign. Let's continue, say here, and be a little bit more explicit about it. Okay. So more or less everything I said is chapter 1 of Green-Schwarz-Schwitten, in case something is not familiar. But I think almost everything I said is there. Okay? So the Green Book of string theory. But if you came to string theory, probably this is roughly familiar, and I just want to give you some I want to just remind you of some general picture. Now, let's be a bit more rigorous. So what do we mean by this equation? Let's summarize this kind of blah blah in some formula. What we are saying is that string theory is defined by a sum over topologies of given genus G. Then we average each topology with some power of the string coupling, and as we will see, or I will tell you, and we can justify it in a minute, the right normalization is this. So as we increase the genus, or as we increase the number of external particles, we should weight it with the higher power of the string coupling. So this is called the string coupling. And then what should we do? For each fixed topology, we integrate over all surfaces of genus G, all two-dimensional surfaces of genus G. This is this integration over X. And we average what? We average a bunch of vertex operators, V1 up to Vn, with some action, exponential, of minus some h bar, which is the string tension, which tells us that if the string tension is very big, strings are roughly classical, and if the string tension is not very big, we have to sum over surfaces, times some action that depends on this map X, and this S of X would be typically something like an integral of, there could be some metric, G mu nu of X, d alpha X mu, d beta X nu, gamma alpha beta. So just to remind you, so this is the worldsheet metric. This is the metric that I choose to put a grid on my worldsheet, on my two-dimensional surface. I draw lines of constant time and constant space, and I need a two-dimensional metric on the grid, on the two-dimensional grid. And this is the space-time metric where mu and nu run over 10-dimensional indices. So this is the background, the curved background where my string is. It can be flat space, or it can be some curved background. Okay? So this is the background, and this is the worldsheet metric. And there are typically more terms. Let me write some representatives, some ones that are very common. There can be some field B mu nu, and the difference is that B mu nu appears not with the worldsheet metric, but with the antisymmetric epsilon alpha beta, and then otherwise it's the same, dx dx. And finally, we can have some dilaton, phi also of X, times the curvature of the two-dimensional surface. Okay? So, and these guys here are backgrounds. These could be background fields. Typical example is flat space, where we typically put phi to be a constant, b to be 0, and g to be eta mu nu. But if you put string theory in a curved background, you typically turn them on. And here I'm ignoring fermions. So this guy here is, as we said, a two-dimensional conformal field theory. Theory without scale. It's a two-dimensional conformal field theory. These vertex operators are operators of dimension 1,1 that I put on this conformal field theory, and I compute correlation functions in this conformal field theory of such vertex operators, and that's the definition of string theory. Okay? Very good. So a few more comments. So large tension, large string tension. What does it mean if the tension is very large? Well, actually, we should keep in mind it can mean two things. What picture should we draw if the tension is very large? There are two natural pictures. One picture is that the strings are very small because the tension is very huge. So if the string tension is very huge, it wants to shrink the string, right? You put the rubber of very huge tension, it shrinks it to a point. And then it's describing something, some string interactions where the strings are very thin. So from where you are sitting, you are from far away, this almost looks like a particle. So it's a point-like particle limit of string theory where strings are very tense, so they are like points and they interact. Okay? But it depends on the boundary conditions of the string. So this is indeed a field theory limit where the strings become very point-like. But imagine I consider the path integral with fixed boundary conditions, and I say that I have, say, an open string where one endpoint of the string is in this line and the other endpoint is in this line. So I'm forcing the string to be big, to be stretched between 2 points, right? So if I force it to be big, it fluctuates here, but if the tension is very big, it just stretches to the minimal solution, okay? It goes to the solution with a minimal area. So it depends on the boundary condition. So if we impose that the string ends on these lines, then it will form some minimal solution, for example, where this would be some minimal area surface. But in both cases, it's a simplification. So either the boundary conditions are such that we impose that the string is big, we force it to be big, and then it will be just some geometrical problem of finding what's the minimal area of this surface here. Or if we don't force the strings to be big by either boundary conditions, another way of forcing them to be big, for example, is spinning the string a lot. If you spin the string a lot with a huge spin, by centripetal force, the string will start to open like a rod. And it will have like a rod spinning very fast, and it opens up. So either you force it to open by giving it lots of spin or by stretching it. And in that case, it opens, but still in a simple way. Namely, if the tension is large, it opens and forms a minimal area surface. Or if you don't, if you just take a string and throw it in this room, it will be a small point that will move in the middle of the room. Okay? So this is the kind of simplification that we get. Whereas if we have small string tension, then we really have to integrate over all possible string surfaces, and they are fluffy, and these strings vibrate a lot, and all stories of the string are important, and there is no particular simplification. It becomes a complicated problem, but still a simpler one than dealing with physics in 10 dimensions. We have to integrate over 2-dimensional maps, but we do have to integrate over them. Another beautiful feature of this description is that if we impose that the 2D quantum field theory that I wrote there is, if we impose that it is a CFT, this means that the corresponding beta functions are equal to 0. Right? That's what a conformal field theory means. It means that if you have some couplings, and if you change your scale, nothing changes. But now what are the couplings? Now be careful. The couplings are this G mu nu, B mu nu, and phi of x. Right? So we want to introduce some scale and check that the beta functions associated to this G, for example, and so on, are equal to 0. Okay? And when you do it, you get some equations that tell you under which conditions, what are the form of this G, what are the form of this B, and the form of this phi, such that this beta functions could be 0. And imposing that the beta function is equal to 0, it tells us that G, for example, obeys, generalized because there are more fields, but basically obeys Einstein equations. So it's nice that string theory, you cannot put it in any background you want. You put it in a background, some background, and you ask, is this background good? And you check, does it define a conformal field theory? No, typically it does not. If you put some random metric, it does not. For which metrics does it satisfy is it a good CFT? For those that obey Einstein equations. Okay? So it's very beautiful that inside it contains this low energy gravity, and that's also another reason why people like string theory quite a lot. Okay? So this is yet another nice feature of string theory. Another nice feature of string theory you can observe by this dilaton here. So let me remind you that in 2 dimensions, gravity there is no degrees of freedom. So what happens if I integrate the Ricci scalar, just the Ricci scalar, over some 2-dimensional surface? Does someone know? What happens if I take the Ricci scalar and integrate it over a surface? Exactly. So all it does is it measures the Euler characteristic, the genus of the surface. So if I change phi by phi plus a constant, So changing phi, that's this field, this dilatant field, goes to phi plus delta phi, where this is a constant. This is equivalent to changing, it's equivalent in the action to adding a constant times the Euler characteristic, so it's equivalent to shifting the string coupling. You see? If you shift the string coupling, it's the same as just shifting the value of the dilatant. That just shifts up to a normalization. Okay, forget about this n. You see, this is the Euler characteristic. I mean, if you have boundaries, it also works. The Euler characteristic contains the n, so we don't need to forget about it. But you probably only remember this part. So if you remember the usual Euler characteristic without boundaries, then if you shift the dilatant, you put in the exponent some contribution proportional to this combination. So this is equivalent to changing the string coupling. And this is why you read in books that in string theory, actually there is only one coupling, which is the string tension. Because even the string coupling, I can think that the string coupling is nothing but the background value of the dilatant. If I change the dilatant, I can change the string coupling. So it's not really, there are the various string theories with various G strings are the same string theory with various backgrounds of the dilatant. I change the background, I don't need to change the theory. It's the same theory, but it's the background of a field that is giving me the string coupling. Okay? So I could start without putting any factor here, and then give you a theory and say the dilatant is some number, and then you know immediately that that number appears to this power here outside, and I can just take it out. Right? So I can think of this as being given by the dilatant there. Okay. Another comment that I would like to make is the following. Suppose I take this vertex operator for a graviton and put many gravitons. I take a graviton, I start in flat space, and I put many gravitons. Then something that could happen is that I'm starting to consider some interactions, and I decide to study some string, and I put many gravitons interacting with this string. Okay, so these guys here are gravitons, and this is some mode of the string, some heavy mode. I don't know. It can also be a graviton. It doesn't matter, but it can be some other string. And I put many gravitons, and I try to make some kind of coherent state of gravitons. I put many of them, and I put some kind of, I'm going to be very schematic, but I put some, they are all indistinguishable, so I put 1 over n factorials times the vertex operator for a graviton to the power n, and I sum over them in the path integral. I think I put any number of them, and they're all indistinguishable. So what would this happen? This would mean that they would exponentiate and deform my action by the integral of some deformation, let me call it h mu nu of x, times d mu of x, d nu, d of x, d bar of x nu, where this thing would come from simply exponentiating the vertex operator that we wrote before. And this h mu nu, if I scatter all gravitons with the same wave, with the same direction, it will be like a gravity wave in some direction, but I can consider gravitons in many, many directions. I can consider various complicated coherent states. But what I want to point out is that it naturally, by putting gravitons, I naturally deform the background. You see, if I had started with eta mu nu, by doing that, I would change to eta mu nu plus some background. And of course, it's better be so. It better be consistent, that I can either change the background by putting many gravitons and let the backgrounds change the geometry, because gravity is just gravitons. Or I can change the background directly from the get-go and just start immediately with the deformed background. In practice, this is very hand-waving. We don't know in practice how to use this kind of cartoonish picture to go from one background to the other. That would be great, but it's very complicated. But morally speaking, something like this should work, and I'm just telling you roughly what's the picture. You just put many, many gravitons, it exponentiates, and it deforms the action by something proportional to dx dx, which is exactly what we need to generate some background. Okay? Just the rough qualitative picture. And indeed, this is yet another way that you could use to arrive at Einstein equations. So you could ask, once you compute these beta functions, you see, you get some equations of motion for some equations that these background fields must satisfy in order for the beta functions associated to them to be 0. Okay? So you derive some equations for this metric G, for this field B, and for this field phi. Then you ask, okay, I have some equations. Let me think of these equations that are just a condition that the beta function equals 0. Let me think of them as equations of motion. And then I ask, from which action could these equations of motion follow? And I write down some action, like the generalization of Einstein equation, of Einstein-Hilbert, like square root of G times R plus dot, 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 where dot, dot, dot are some kinetic terms for B and for phi and so on, right? So I write some action from which this beta function equals 0 condition follow as equations of motion. This is what's called the string effective action. It's the action from which I use to find out what are the good backgrounds of string theory. How could I derive the action in some other way? I could say there is some action, and I write everything I can write, which is diff invariant and good. So I write Ricci tensor plus kinetic term for B plus kinetic term for phi plus interaction and so on. And then I don't know the coefficients, because just by symmetry I cannot fix the coefficients. How would I fix the coefficients in an action? If you give me an action, how do you fix the coefficients? Well, you do an experiment like at the LHC. You scatter a bunch of particles, and you see some scattering process measures a precise coefficient, and you compute the scattering process independently, you match the two numbers, and you read off what the coefficients should be. So another way of fixing the coefficients of that action is you know how to compute scattering amplitudes. This was the beginning that we said. You compute them, you see what you should get, and you see what coefficients should you fix in this action to give the same results. And the outcome of doing this is you arrive at the same action that you would arrive in this way. So it's kind of a self-consistency picture of string theory. It better work, and of course it does work. Okay? Okay, so finally, this is whole hand waving. This is whole, I mean, not hand waving, but I'm just giving a qualitative picture. Let's do some simple but more concrete computation of understanding why this particular power here. Okay? So just to relax a little bit after all this firework of ideas, let's do something simple. Let's think a little bit about this exponent here. Okay? Okay. So was it our choice, or did it have to be like this? Was it crucial that it was this 2G string minus 2 plus n, or could it have been something else? Okay? So we are saying that we get 2G string to the power twice the genus minus 2 plus the number of particles. Okay? And the claim is that indeed this had to be this. Okay? There was no option. But let's do first a consistency check. Let's consider the case where I have one particle that splits into two and joins again. But let's think that this process I can get by taking two pair of pens and joining them together, right? I take two pair of pens and I glue them. And let's check that thinking in both ways, I would reach the same power of G. It must be. Otherwise, I will start getting inconsistencies as I start cutting my string processes. So let's count the coupling power. So this guy has genus G equal to 1, and it has two external particles. Well, whereas here we have twice, because we have the lower and upper pair of pens. And then each pair of pens has genus equal to 0 and then equal to 3. So in total, here I get a power of 2 minus 2 plus 2 equal to. Whereas here I get a power of 2 times 0 from the genus minus 2 plus 3, which is equal to 2. Okay? And in fact, even though this looks like a simple example, the generalization for any genus and so on is rather straightforward. And you can easily see that the only combination, so first notice that here, if I know that it grows with n and with g, there are only 3 constants. What is the constant that multiplies g, what multiplies n, and what is this minus 2? Of course, this, you can easily see that if you make such ansatz with a times g plus b times c times n, by requiring consistency over gluing in many ways, you see that this is the only combination that could ever work. Okay? So let me give you, let's work out another simple example to see how this would work. Suppose I consider, for example, a 4-point function, a 4-string amplitude of a genus G. Okay, I consider such surface. Okay? And let's see how this would be consistent with cutting this into several pair of pens. So if I cut it into a pair of pens, let me cut it in this way. Like this, like this, like this, like this. You see, this is a clever way of cutting where I really cut everything into pair of pens. Do you agree? How many pair of pens do we have? If we have genus G. So this is 1 hole, 2 holes, G holes. So I have genus G. How many pair of pens do we have in this picture? How many? So someone said 2G, and then plus some constant that I cannot hear. But 2G is a good starting point because each hole has 1 pair of pen to the left and 1 to the right. 1 to the left, 1 to the right, 1 to the left, 1 to the right, 1 to the left, 1 to the right. So 2G is a good starting point, but it's not correct. What should we do? Plus 2. There's the first and the last one. Plus 2. Right? This is the number of pair of pens. And each pair of pens comes with which coupling? Well, each pair of pens comes with this power of G string that we computed here, which is just 1 power of G string, so times 1. Okay? So in total, this is what we get, 2G minus 2. And indeed, if I plug into this formula, now 2 genus minus 2 plus 4, this combination gives exactly plus 2. Okay? So this is just another example, but you can easily convince yourself that the only possible combination I could write would be precisely this one. Okay. Okay, last comment about string theory that fits in this corner here, which is suppose I have a closed string that goes, so this is a closed string that is emitted here and absorbed here. Okay? So what are the objects that emit closed strings? D-branes. Is it clear to everyone? Does everyone know this name, D-brane? D-brane is the object, a plane or an hyperplane that can emit closed strings. So I should draw some plane here and saying that this plane emitted a closed string that was absorbed here. Okay? So this would be a D brane. By definition, it's the object that emits open strings. But this is a closed string, but now think a little bit from some other point of view. If you don't think of time going in this direction, but if you think rather in Euclidean time going in the circle, from this point of view here, it looks instead that I have an endpoint of a string, an endpoint of the string, and the string is stretched between two branes, and it's going around in a circle. It looks more like an open string here. And indeed, you might describe this process either as an open string partition function or as a closed string propagation. And they are just the same, because indeed, depending on how you see the surface, they are the same. So we have this interesting open, closed duality in string theory. Okay? Whereas as soon as you have open strings, you automatically, where string theory, even if you did not know about closed strings or about open strings, as you start discussing strings and looking them from different points of view, if you did not know about closed strings, you would find them. And if you did not know about open strings, you would find them. And some people can describe some physics purely using open strings. Someone purely using closed strings, they think they are talking about totally different things, and they are talking about the same thing. Okay? And this is just totally fine. There's no contradiction with it, but it's another important concept. Okay, so if some of these topics is totally unfamiliar, do feel free to come to talk to me at the end, or just refresh your memory a little bit tonight. But now we switch gears a little bit, and we will come back to various of these points during the course. But now I'll switch to what's called the large N limit of quantum field theories. Did you discuss this in some of the lectures? The limit where we take a quantum field theory with a large number of colors, like imagine QCD, where we have 3 colors, but we take the number of colors to be very large. Was it something that you discussed? Yes? You did?
It was a tutorial.
Ah, okay. So, okay, we can be fast then. Good. But really, before I move, because it really is a different topic, so here are the 4 blackboards. They're all visible. I would encourage a question or two. While I see if I forgot something.
Here's a question.
Yes?
When you say that background must obey the Einstein's equations, is that linearized around something?
No, it's a full nonlinear Einstein equations.
But you say generalized. What's the generalization?
No, generalized just means that you see now here we have a bunch of fields. It's not just a metric. It's not a set of equations just for the metric. It's an equation for the metric, but it will couple with the B field and with phi. So you have a theory which now doesn't have just graviton. It has graviton. It also has an antisymmetric field, B mu and u. And it also has a free scalar, a free massless scalar, which is the dilaton. You see? So you would say, can I get just gravity and nothing else? We don't know very well what string theory describes just gravity and no dilaton or no B mu and u. It's tough. But as a particular solution, you can set the B to 0 and phi to 0 and look for solutions that just contain chi, and those would be Einstein equations. Yes?
The people, like on the S matrix side, do people ever look at like just normal QFT, then say like let's assume these things are strings, and then say like, well, the low end limit we want this to be independent of the string length, and then use this as a renormalization technique, or? Because you say there's no dangerous UV divergence, like I would like.
Yes, yes. So I'm not sure I understood your question, but let me say, so you can ask, can I construct in string theory something which is not just scattering strings, but something more off shell, like correlation function of strings? I put some strings at some positions and so on. And it's much tougher. And this is something that people like Sen and others are investigating now. So there is a huge jump in complexity between describing asymptotic observables in string theory and local observables, like off-shell observables in string theory. And it's unclear whether this is something deep and whether it's a bug or a feature. Because in quantum gravity, we don't want local observables, because it does not make sense to say what's the correlation function between a field here and a field here, because if a metric is changing, what's the notion of this coordinate and this coordinate? I mean, there's no notion. I mean, the metric is changing. So only asymptotic questions you can ask. So perhaps it's a feature, but perhaps it's a bug. So the space of questions that string theory allows you to ask her, is smaller than the set of questions that you could ask in a quantum field theory. Perhaps it's good, or perhaps it's bad. We don't know. More questions? Maybe let me ask you, is it true that like 80% of this was covered in string theory? Or 70? Yeah? You don't remember. Okay. That's fine. Okay. So now we discuss large NC. Okay? So theories with a large number of colors. Okay? So let me remind you that in the real world, so in QCD, NC is equal to 3, which is big, but not huge, but it's big. And in fact, it's big, and many approximations that people do based on large N analysis, many analyses on phenomenology, like which baryons could decay and form which mesons and so on. If you just do some very naive large N analysis of QCD, you explain many of the phenomenological properties of QCD actually with like 20% accuracy. So it's not so bad to say that N3 is large. But okay, so what's the Lagrangian of pure glue? So just gluons. Well, pure glue would be proportional to, there would be 1 over G Young-Mills square trace of F mu nu, F mu nu. Okay, and okay, if it's not pure glue, if it's glue plus other stuff, there will be plus other stuff. Okay, pure glue is just F squared. Okay, there could be some matter as well. Okay, so now suppose I ask, how does my coupling change as I vary the energy scale? So as I vary my cutoff or the energy scale at which I measure my coupling. So this is the beta function where we get that this is proportional to this quantity. And then there is the famous 11/3 that you get from pure glue, plus some extra contribution if there would be matter. Okay? And this is the beta function. So now let me use this to try to ask what happens if G Young-Mills, if we are at very small coupling, we want to do perturbation theory, but the number of colors is large. Okay? So we want this guy to go to 0, this guy to go to infinity, but in practice, okay, one is very small, the other is very large. Okay? Now, what would happen? What would happen is that you see that if I start with some G Young-Mills very small, and I ask, I vary my scale a little bit, what is G Young-Mill after varying this scale a little bit? It changes a little bit, because I vary a little bit, by this little bit. Okay? So this is the amount by which it changes. Now, if G Young-Mills is super small, and then is very, very large, but N is much bigger than G Young-Mills, like N is the number of, okay, it's a huge number, much bigger than G Young-Mills, then even though G Young-Mills is very small, it increases a lot. Okay? So what combination likes to be kept fixed? Well, that's easy. And indeed, if you multiply this with a small algebra, you really see that you get dd mu of lambda is equal to some constant times lambda square, where lambda is G Young-Mills square times n. So it's a combination which is called the 't Hooft coupling. And this is the combination that if you start with it of order 1 and you evolve a little bit, it stays of order 1. You see? You construct the right combination that as you are changing scales. So this is a way of motivating us to look at theories and to study these limits where we take this Tooth coupling, we held it fixed, while we send G and mil to 0 and then to infinity. You see, once again, let me repeat. Suppose G and mil is very small, and n is very large, but n is much bigger. Then what happens is that after a little bit of step, now suddenly G and mil is a bit bigger. Now, and you can see that if you evolve a little bit, after a few steps, what will happen is that lambda will become of order 1 and then continue to be of order 1. Okay? So if you start with a lambda which is too small or too large because this combination is too huge or too small, then you will naturally tend to increase a lot or decrease a lot G and mils in order to make this combination of order 1, because you see that this is the equation that doesn't have any power G and mils or n. Okay? So this is kind of a hint. And this is true in any theory which has a large number of colors. This was an example of QCD, but if you have other large n theories, the beta function will have this schematic form. The constant will, of course, change. QCD has this nice negative number that gives us asymptotic freedom. But the conclusion that this would be the nice limit to take would remain. Okay? So this Tooth coupling is the relevant, seems to be the relevant combination if I want to get an untrivial limit where even though I send G and mil to 0 and then to infinity, something remains fixed and I still get some interesting dynamics. So this would be the first example, the most typical example of large n theories. And we would love to be able to solve this theory, even in the large n limit. Pure glue is a very tough theory. Pure glue, what's the dynamics of pure glue? You just have gluons, but the gluons are self-interacting. So what happens to the gluons? Two things can happen. You can scatter them if you are at very high energies, because at very high energies, gluons are approximately free. So if gluons are approximately free, at very high energies, you can scatter them. They fly, they scatter with each other, and they live. This is what you do to compute scattering amplitude at the LHC. Because at the LHC, when you scatter, say, a nucleus, the nucleus is a bunch of, it has a bunch of quarks and so on, connected by gluons. And at very high energy, it's often the gluons that are scattering. The quarks just fly, and it's the gluons that will scatter with each other. So you prepare some particles, you throw them at very high energy, you consider the process of scattering the gluons, and this gives you what's called the hard part of the scattering process that you measure at the LHC. But on the other hand, at low energies, the gluons are not free. You cannot observe gluons. Gluons, they form sticky stuff. They form balls of glue ball. You imagine some tubes of gluons that form some fluffy ball of glue. Or if there are quarks, they keep the quarks together and they form mesons and baryons and matter. So what happens is that at very high energy they scatter. They have a scattering amplitude for scattering the gluons. Boof, boof. But then as they fly apart, they form jets and they form a messy stuff as they cool down, if you want, as the energy starts to decrease. And what you receive in the detector are tracks of garbage, like a bunch of protons and baryons and mesons and some tracks of stuff. Okay? And you have then to join the hard part with the soft part, and in this way, and this is a complicated process that goes from the high energy part to the low energy part, where you start having more phenomenology and so on, because the dynamics of weakly coupled, of low energy QCD is very, very complicated, and we don't know how to do it analytically because the theory is strongly coupled. So what would you ask at high energy? As we said, we ask about scattering of gluons. What about at low energy? What's interesting to ask about this theory? Well, what's interesting is you form these glue balls, these balls of energy, these balls of glue. There is an M1, an M2, an M3, which are the various glue balls that you can form. And you can ask, what's the ratio M2 over M1? What's the mass of the second glue ball over the mass of the first glue ball? This is a pure number. People measured it, like 1.4 or something, I don't know. It's some number. This number is a number we should be able to compute from this Lagrangian. And no one knows how to do it. It's a strongly coupled theory, it's hard, even in the large n limit. Okay, this is a very interesting theory, but as I said, it's a very interesting, very rich theory. It has a beautiful physics, but I want to consider a simpler one. We should consider simpler theories first, and then we'll come back to QCD in a few lectures. So another example, a simpler example that we will use to study this limit of a large number of colors. Another example would be, take a Lagrangian where you consider some field phi. So this is a matrix valued scalar. This looks a bit confusing. Scalar from the point of view it has no index, there's no spin, but it's a matrix. Okay, and we can see some kinetic term, d mu phi bar. So this can be a UN matrix. Okay, so it's a matrix. We take trace over these n by n matrices, like in QCD. Okay, and there can be some coupling. Plus, so the coupling I'll put, like in QCD, I'll put 1 over, I'll call it Jiang-Mill square, just because it's the name I want to give it, plus C3 times some phi cube plus C4 times some phi to the 4. Okay. Suppose I consider this here. Okay. Okay, good. So first let me just remind you, some people get confused by putting the coupling here, but this is the standard thing. In quantum field theory, often we can put the coupling in front, and weak coupling means really weak coupling. Jiang-Mill is very small. So for example, if you rescale, let me do it explicitly because otherwise some people will be confused. If I rescale the fields, I can write this as trace of d phi tilde square, the kinetic term. So I rescale phi to be g times phi tilde, and then what do I get? C3 times g times phi tilde cube plus C4 times g square times phi tilde 4. Okay? Now this is familiar, right? So now the coupling is in the right place. Okay? But I like this one better, so I'll use this one. Okay? Okay, so now let's study a little bit this theory. And what we are interested is in considering what happens to this theory if I consider this 't limit, where I take this, our goal is to take what we will study is to take lambda fixed with NC to infinity and Jiang-Mills to 0. Okay, so from the kinetic term, we derive the propagator, and we conclude that what's the propagator? The propagator is what's the correlation function? Phi ij phi kl, where these indices, now I'm highlighting that these guys are matrices. So they have some indices ij that I did not write here, but when I write phi cube, I mean phi times phi times phi. Okay? So what's this propagator? Well, this propagator, before writing the expression, let me write the picture. I want to say that this, I want to use the double line notation to indicate that each field has two indices, an I and a J, and a K and an L. Okay? And I put the index which is upstairs, coming with the arrow that leaves the index upstairs to the index downstairs. And this could be at some position X, and this could be at some position Y, for example. And then this propagator would be what? Would be Jiang-Mills square, okay? Because it's the inverse of what's here, and here there is 1 over Jiang-Mills square, so this propagator becomes proportional to Jiang-Mills square, times delta IL delta JK times some space-time dependent, which is not relevant, but okay, if you want, in 4 dimensions it would be 1 over x minus y squared. It's the propagator of a massless scalar in 4 dimensions. But this particular space dependence, let me call it g of x minus y, is irrelevant for what we are discussing now. So don't worry about it. What matters is this first part here. Okay? So this will be our propagator, while What about the couplings? What about, say, this cubic coupling, this trace of phi cube? How would we represent this trace of phi cube, this vertex? We want to start drawing our Feynman diagrams. And this vertex, trace of phi cube, we will draw it again in double line notation, like this, where we would say, for example, this would be index I, this is j. This would be then index j, this would be index k. Right? And by this picture, we mean what? Let's see. So we mean here scalar phi index up I, index down j, index phi index up j, index down k, and here phi index up k, index down I, which is indeed nothing but what we mean by trace of phi cube, right? It's just the product of three matrices and trace. Okay? So you see, we use this notation for vertices, this notation for lines. So all we are doing is fattening. It's a fat graph. We are just taking the usual propagator, which is a line, and we fatten it into two, and take the usual vertex, and we fatten it into some ribbons. Okay? Okay? And similarly, trace of phi to the 4, we will now represent by a cross, etc. Okay? And now we draw graphs with these fat graphs. Now we start drawing our Feynman graphs, where now the propagators and the interactions have these fat graphs. Any question here? Should I continue here or erase and continue there? What do you prefer? Sorry? Speak up. Erase or continue here? Yeah. Continue here? Yeah. Okay. So let's consider a vacuum diagram. Right? So a diagram, just a vacuum. So I could just partition function. I consider all bubbles and so on. So a vacuum diagram with V vertices, E propagators, which I call edges as well. I have vertices and I have edges between the vertices, and F closed loops of color. Let me explain what this is in a minute, which I will call faces. So let me illustrate what this is in a graph, but it will be clear. So imagine I consider, say, a vacuum diagram obtained by joining two vertices phi cube, and I will draw a graph by uniting them like this, and like this, and like this. Right? So this is just a fat version of some graph that you can do easily. And let's see, what would be this diagram? This would have? This would have two vertices. How many propagators would it have? 3 propagators, right? 1 here, 2 here, 3 here. And how many loops of color? Loops of color are how many closed lines there are. How many are there? 3 closed lines. And why do we call them faces? Because imagine putting this graph on a sphere, and imagine that I want to put, these are like frames, and I want to put windows here of glass. So I put here a piece of glass that covers this part. Then I put a piece of glass that covers this part. And if the outside is just a sphere, I put another piece of glass that covers the outside. Okay? So these are faces. If I think of this graph as some triangulation, these are faces. That they are the faces of the graph. So this is one face, this is another face, and the exterior is another face. But it's the number of closed lines. Okay? So a vacuum diagram with these propagators scales as, so how does it scale? So the number of propagators, I get something to the number of propagators, which is edges. With what weight? Well, each propagator comes with a G Young mu square, you see. But G Young mu square is nothing but lambda over n. Then I have vertices. Each vertex comes with what weight? Well, if I expand the vertex, it comes with the inverse, 1 over G Young mu square. So it comes with the weight, which is n over lambda. And how many? And then there is faces, and each face gives me a factor of n, because I sum over the color index from 1 to n. Do you agree? So let's see this example. This example here, I have n from this face, n from this face, n from this face, and I have from this vertex, I get 1 over G Young mu square, and from each of these propagators, I get G Young mu square. So in total, you can easily see that this would go like n squared times lambda, right? Yeah, n squared times lambda. Okay, so this is just a simple example. Okay. Now another example, this is one example, and then here is another example. I take a 4-point vertex now, and I will draw this diagram here, where I will unite this, and then this line, I have to draw it going below the other one, and I'll draw it like this, okay? So this is another example. And if you check how this diagram scales, you see that this diagram scales like n to the 0 times lambda. Okay? So the key difference is that one diagram scales like n squared, and the other diagram scales like n to the 0, so no power of n. And what's the key difference between these two diagrams? Is that this diagram is what's called a planar or sphere or genus 0 graph. It's a graph that I can draw on a plane or on a sphere. As we said, we can put this diagram on the surface of the sphere, on the surface of the Earth, and just draw it there. Whereas this diagram, to draw it without lifting the paper, I cannot. You see, this line needs to go on top of it. This diagram, I need a torus to draw it. Indeed, if I have a donut, I can draw this graph. I can draw the graph like this, right? You see? So on a torus, I can draw it, but not on the sphere. So this graph is a genus 1 or torus graph. And it seems like spheres are more important than torus. Like spheres come with a bigger power of n. And indeed, it's not a coincidence, because in general, we have that in any graph that you can triangulate a two-dimensional surface, the number of vertices plus the number of faces minus the number of edges is 2 minus 2g. Okay, so there is a simple relation between these numbers and the genus of the surface. And therefore, these vacuum diagrams, this partition function that you would consider, you could write it as a sum over genus G, 1 over n to the power 2 genus minus 2 times some function that depends on the genus and that would depend on lambda. Okay, you can easily see that the powers of n, as they are here, you see, they group to form this simple combination, and then the summation over the edges and vertices and so on will lead to some function of lambda. So pictorially, we say that we are summing vacuum diagrams, and we sum all the diagrams that I can draw on a sphere. I draw all diagrams that I can draw on a sphere, plus all diagrams that I can draw on a torus, plus all diagrams that I can draw on genus 2 torus, and so on and so forth. And these diagrams come with a power of n squared, these ones with power n to the 0, this one n to the minus 2, and so on. Okay? And this is already smelling like a string theory. This looks like we are summing over topologies, and for each topology we sum over all graphs of the same topology. We were using very similar words before. We were saying we sum over topologies, and for each topology we integrate over all possible surfaces. And now we are using the same words, but instead of saying we sum over all possible surfaces, we sum over triangulations of those surfaces, which morally speaking should not be so different. So we are approaching something deep, and indeed we are. But let's go on and see if we can make this analogy even closer. So this was for vacuum diagrams. Okay? But now, let's go from vacuum. Let's try to make the analogy even stronger and go to insertions. Okay? So let me continue. So suppose, can I continue here?
Yes.
Yeah? Suppose I consider some operator, trace, of phi to the j. Okay? So this is my operator. So what picture do I associate to this operator? Well, trace of phi to the j, you see, you draw it as a vertex, say, let's suppose j is 5. You draw it like this. Right? So this is phi to the j when j is 5. Or, let's draw a bunch of pictures, they all are the same thing. Or, for example, I can think that I'm drawing a circle here and seeing what is coming up. And I can also draw like this. If all I want is to keep track of the indices, I can also draw it like this. You see? Where this is just keeping track of the indices, but I should remember this is inserted at some position x of space-time. All these points at the same position x of space-time. Or, this is the same. I can draw it also like this. I can draw, let me try. You see, I just drew a circle with 5 lines coming up. But I remember that all this is at some position x. This is just a mnemonic. It's like a tube coming in. Right? Or I can now forget about double line because it's becoming hard to see, and I can just draw the circle with 5 lines going up. Okay? Or 5 lines coming up, provided I know I should fatten them up and so on. So there are all these ways. But all of them, depending on your taste, they are the analog of inserting a tube, a closed string. They have all the topology of a cylinder that I'm inserting here. In the same way that before it was the vacuum, now these correlation functions of these operators would be like inserting strings. So a 2-point function, OO, for example, would look like if I have a cylinder and I just connect the various fields. Now I'm not fattening the lines, you should imagine that they are fattened. And then drawing all possible interactions in this cylinder and so on. Okay? But this would have the topology precisely of inserting some operator at some position and receiving it at some other position. Okay? This is just a picture. It's the same picture as drawing this, 5. Going to 5 and just uniting the propagators and starting putting some further interactions here. And you see, these interactions from the topology point of view, if I remove a bit of space here and here, it's a cylinder. It's a cylinder going from one place to the other. So now let's consider what's the correlation function if I have n of such operators, O1 up to On, and I ask what's the connected endpoint function. Okay? So you just draw all connected graphs. Can you read there? Phi 1 up to phi n of n such operators. And let me tell you what you find. And you can easily see, you repeat the same analysis. It is just the same thing because this is nothing but a vertex. But it doesn't come with any power of n, so there will be an extra factor. And that factor will be nothing but saying that you have to sum over the same genus G. But now you have 1 over n to the power 2g minus 2 plus n times, for each genus, some non-trivial function of the 't Hooft coupling. Which means, of course, that we have our 3 operators, like genus 0 plus genus 1, and genus 0 comes with G string. Genus 1 here would come with G string cube plus dot dot dot. So we are reaching a very powerful conclusion. And the conclusion is that, or conjecture, is that large n, and I'll put gauge and I'll comment maybe today, maybe tomorrow, large n gauge theories, these theories with a large n number of colors, large n gauge theories are string theories. In other words, if we manage to be powerful enough, we should be able to think about these large n string theories in terms of a string theory, in terms of saying that what I'm doing is summing over topologies of string. And what replaces my path integral over shapes of my string surface is the summation over all diagrams of a given topology. You fix the topology, you draw all diagrams that fit on that topology, and the summation over those diagrams is the analog of integrating over all possible surfaces with a given topology.
Well, why do you need large n for that conclusion?
I need large n in order to have an expansion parameter G string. Because in this identification, G string is nothing but 1 over n. You see, it's what appears here, weighting exactly this factor that we saw in the beginning. That we saw there, on top of the box.
It's always an expansion in that regardless of the value of n, right?
It's always an expansion in that, yes.
So you don't really need large. I mean, it's preservative for large n, but...
Yeah, that's right.
Okay.
So n equals 3 would still...
It would, but it would be a very quantum string theory, where the probability of splitting is not so small.
But then
so it becomes a harder string theory to deal with, yeah. Yeah, we don't even need large n, yeah.
But we can still expect like these spin 2 states out of QCD, like...
No. No. So I don't think, no, we don't.
Make this,
sorry?
in what sense do you then make this conclusion? Like, if you know, SU3 is already one of your gauge theories which you consider large n, in what sense is this string theory aside from the fact that you can just do this?
You mean if I can make this more precise? That's your question?
Yeah.
In general, that's the challenge. Can we somehow make this more precise and not just say there is some string theory, like existence, but rather can I have some useful string theory that I can use to do something? And that's much harder. Now that you ask, do I know the string dual for any theory? If you give me a theory, I give you the string theory. No, by far. We don't know yet the string theory dual of QCD. I'm saying it should exist. Someone should find it. We do know some string duals. But the message, I think, is that there should exist for any string theory. So there should be some dot, or maybe some exclamation mark, or maybe some comma, or a mixed combination of this. Okay? This should be definitely, that's basically what we expect. And in the last 5 minutes, I just want to, do I want to? No, maybe I'll stop here and and tomorrow pick it up and summarize a little bit what we have done. But let me just summarize a little bit by words. So first we started by saying what is string theory? String theory, as a perturbative definition, is a summation over two-dimensional surfaces of given topologies. So we sum over topologies. We consider first the strings that dominate are the ones which have no holes. Then you have a string with 1 hole, 2 holes, 3 holes. And we sum over the genus. And for each genus, you integrate over all possible stories of the string. Where you fix the genus, you say, for example, the string has 1 hole. It means that at some point it splits and joins again. But the shape of it can fluctuate a lot or be almost straight. It can do a lot of things, and we integrate over all possible surfaces. Now we see that in large n gauge theories, or in gauge theories when organized as expansions in 1 over n, we are doing something, morally speaking, which is the same. For each fixed number of operators, which are like insertions of closed strings, so we scatter like 3 closed strings, and what we should do is draw a sphere first, and then triangulate the sphere in all possible ways. Draw all diagrams I can draw on the sphere, like the one we drew there, one with more cubic vertices. All those graphs that I can draw on the sphere will scale like n squared. Or sorry, well, I have to work out like 1 over n. Will scale like 1 over n for 3 points, right? And I should sum over all of them. And this is the analog of saying I fix 3 points and I sum over all possible shapes. So if such duality exists, and if we can make it precise, for example, you expect that this Tuft coupling lambda should be related to a string tension. Because for a given topology, what governs the summation over different shapes and what tells you which shapes are more important is the string tension. If the string tension is very large, it's mostly about classical string configurations. If the string tension is very small, we have to sum over all such configurations. Here, similarly, if I take for a given topology, the Tuft coupling tells me how complicated is the triangulation, and I expect triangulations with a huge number of vertices and edges to look more and more like a smooth surface. So I expect that this sum over diagrams, especially when the Tuft coupling becomes very large, I should approach a classical string description. And then I have genus 1 surfaces, which should correspond to strings with 1 hole, and so on and so forth. So if we could make this precise, we can already anticipate that this duality should be powerful but hard to check. It should be powerful because what we are saying is that the diagrams that look more and more like smooth surfaces are diagrams with a huge number of interaction vertices. So very, very dense Feynman diagrams, where I have a surface being triangulated very precisely, like as you do a computer game and you want to put everything very smooth. But those precisely the diagrams where you have infinitely many loops, where you asymptote to the limit of needing diagrams with infinitely many vertices, are exactly the diagrams that you don't know how to compute. Because you only know how to do quantum field theory if you like 3 level, 1 loop perhaps, or in some simple diagrams, right? So if these dualities exist, they will be very powerful because they will be simple in the corner where you don't know how to compute. And they will be complicated. These fluffy strings that fluctuate a lot will correspond to the case that you know very well how to compute. So it will be complementary. If we can make these dualities precise, they will give us the answer when we cannot compute. And using what we can compute, we'll be able to learn about the hardest, most quantum regime of string theory. So that will be awesome. On the other hand, given that there will be no overlap in what we can compute in both sides, how are we going to check whether they are true? Okay? But we will. But not today. Okay, thank you. We'll continue tomorrow.